Good morning, everybody, and welcome to the next in a series of UKDEA webinars. My name is Simon Woodward. I'm the chairman of the UKDEA, and this morning's event is looking at ambient loops networks versus fourth generation heat networks. So a topic we felt was not well understood, a topic we felt we should be discussing and talking about, and hopefully will generate a lot of questions in the chat. We've got over 200 registrations this morning, so I'll give it a few seconds just to allow more people to join, because I can see people pouring into the conference all the time virtually. So we'll give it a few questions. Just while we're going, there's two buttons at the bottom of your screen. One is for questions and one is for chat. We'd be really grateful that if you put questions for the speakers, could you please put those in the questions section? And if you just want to chat amongst yourselves, then please put that in the chat section so that when we get to Q&A section at the end, we've got a nice clear area where all the questions are from the various delegates. Okay, so we're not delayed. I will kick off, although we've still got people coming in at the moment. So just to kick off with the first slide, who are we? Who is the UK District Energy Association? Well, we're a bit unusual. We're a non-trade, not-for-profit association. We were formed 12 years ago by a grouping of local authorities who felt that they didn't have a voice for district energy schemes in the UK. And since those founder members of 6 organisations formed us, back in 2010, we've grown to around 140 members. We've grown rapidly. We've had about 25 new members in the last 12 months. The diagram on the right shows how the UKDEA is structured. So at the centre are 4 members. So those are people who are even developers, owners and partners. And around those are the various associate members, the very important members, the consultants, advisors, service providers, equipment suppliers, contractors, etc., etc. And all the major district energy schemes in the UK are represented by the UKDEA, and our function of our reason for being is to offer guidance and support and to raise awareness of district energy. And a lot of that is about engaging with the government. And I've literally just jumped off a call with BEIS where we're talking about how BEIS can help support the sector with the problems we're experiencing with rising gas prices over the last 6 to 9 months. So on to the next slide. What do we offer members? We really welcome new members. As I said, we've had a number of new members join over the last year. We offer them the tools and support they need to develop their own schemes. I'll just quickly run through those. So as I said a few months ago, we're a respected voice for raising concerns to government. The meeting I've got after this one at 2 o'clock this afternoon is with the Director of Heat Networks. So I meet with him monthly in BEIS to talk about the industry's problems, issues, questions, things that we need to discuss with government. We also publish a 50-page monthly journal to keep members updated and informed about what's going on in the sector. So it's really, it gathers all the news, all the information, everything going on within the sector, and puts that into the journal. We have an annual conference and AGM. We also have regular information networking sessions, working groups, and webinars such as the one today, and that's an ideal opportunity, as a number of our members have chosen today, to showcase your expertise, products and services. And at the end of this brief presentation, I'll talk about the next couple of webinars that we're planning. So again, do get involved. If you're not a member, consider joining so that you can get involved and take part in those webinars. We've got a feature-packed website which has got a library sitting behind it for members to access, which is full of hundreds of very useful district energy documents. And we also work very hard to promote the DE sector through events such as the one which was Future Build 2022, which happened last March. And we're planning another exciting Future Build in March 2023. We've also got a really interesting document, which is the training register, where members can showcase the training that they offer to organisations across the sector. And in 2022, we're launching a series of podcasts and our first awards, which we're really excited about. We've talked about creating UKDEA awards for a number of years, and now we've reached year 12. We think it's about time we should formally launch those. And we also offer help, advice and support. I have multiple one-to-ones with members during the month, and a lot of that is really to highlight to them that things going on in the sector, things that may well have been covered in the journal, but they might not have picked up or might not have had the time to read. But most importantly, we're a network of around 140 members working together to assist each other and as a voice for the sector. So ambient loops versus fourth gen heat networks, bit of a potentially a contentious topic, but we hope it's not. We hope everybody will embrace it in a collaborative manner today, although it might get a bit contentious in some of the Q&As. So we're very aware that there's a lot of confusion in the sector about whether 4G networks are better or worse than ambient loop networks, sometimes referred to as 5G networks. I personally don't refer to them as 5G networks because I don't think they're a heat network per se. They're an ambient loop network, and I think that's the better correct technical term. I think the reality is, from my perspective, that neither is better or worse. In practice, they're quite different technology solutions, and the one you select will depend to a large degree on what you're trying to achieve and what the development is and what energy sources are available, etc. So we've created this event to demystify any confusion regarding the nature and advantages of these two types of networks. Although very interestingly, I picked up only yesterday that the Mayor of London has published the new energy assessment guidance in June 2022. So that only was published last week, and I'll read you a few words from that should just come out. And it actually says that ambient loop systems with heat pumps in individual units are regarded as individual heating systems, and therefore would not be appropriate for developments in heat network priority areas. There is a clear potential to connect to an existing or planned area-wide district heating network, unless confirmation has been provided by the network operator that such an arrangement is suitable. So very interestingly, the GLA has now got quite clearly off the fence and believes that in heat network priority areas, and you can see those on the London heat map, ambient loop systems are not appropriate. And don't forget that today's events, as all UKDEA events are now, certified by CPD, which is really good, so you can claim the credits, and the code for your certificate when it's emailed out to you will be the one shown on the slide there. So this morning we've got four really interesting speakers. We've got Oddgeir from Danfoss, who will highlight the important differences between fourth generation versus fifth generation. We've got Joseph from Comsoft, who will talk about a design comparison of fourth gen and ambient loop systems. And we've got Asad, who's kindly stepped in for Rob Boyer from AECOM. He'll be looking at sustainable heat, should it be fourth or fifth? And then closing with Matthew from Hilson Moran, opportunities and design considerations for fifth generation heat networks now and in the future. And at the end of that, we'll bring it all together with 20 minutes of Q&A. So I'm keen to press ahead because I want to stay on time. Just a final slide before I switch to my closing one. So as I mentioned a moment ago, this is one in a series of webinars. We've been having a large number over the last couple of years. If you want to see the old seminars, please either visit our website or go to the UKDEA YouTube channel. The next two we're planning, the first one will be the role of local authorities in heat network in collaboration with BEIS. So again, this is slightly contentious because there's those people who sit on the side of the fence that local authorities should be developing heat networks through a local authority owned ESCO. And there's those people who sit on the other side of the fence and believe that local authorities developing heat networks through a local authority owned ESCO are the worst thing in the world, and that they should step aside and issue a concession and allow private sector ESCOs to come in and develop heat networks. I have no fixed view. Personally, in my private life, I've worked on both sides of the fence. So this will be a very interesting event, analysing the options and the possibilities for local authorities to get involved in heat networks at all parts of the spectrum, either of the approaches or somewhere in between. And then the one after that, we're planning a repeat of our very successful Innovation Event Showcase. So Innovation Event Showcase number 2, which will allow our members to show to the world their exciting new products, systems, case studies, schemes, etc., etc. If you're interested in attending these events, please contact the Secretary, or if a UKDEA member, do get involved. So that's it from me. If you want to talk about membership, give me a call, drop me a mail. I'm available all the time. And without further ado, I'd like to invite Oddgeir to step onto the stage and to make his presentation on important differences between fourth generation and fifth generation. So thanks very much indeed. Over to you, Oddgeir.
Yeah, thank you, Simon. Well, it's interesting that what you said, that the fifth generation or ambient loop is kind of a different technology. That is exactly how I see it as well. I also don't see it as heat networks for urban areas or cities, so you will have no surprises from my side considering the introduction in that. But I made a slide, so let's go through it. So the district energy here, I would like to start to say, and this is the thermal infrastructure of the future, and why is that, and what are the keys here? That is that we are aggregating the thermal demands, and this can then be district heating or cooling, depending on the heating demand or cooling demand. But there's also the idea is to get a better utilization of energy, primary energy sources that we use, and enable the utilization of local low temperature, renewable energy sources, and waste heat, which might be available in the area. It's also about having a cost-efficient thermal supply for the urban areas. And in recent time, then we have identified district energy as the enabler of the smart energy sector, and also the key to decarbonizing the whole energy sector. And this is what the system should live up to. When we want to talk about generations, then it's important that we have some ideas on why we have defined those generations or how they are defined. And this is important to have a good understanding of before we can compare the ambient loops, the fifth generation, to the prior generations. So the key element is this collective centralized system. And to be able to do that, we need the pipe network, of course, and we need heat plants. And from that point, we can start to think about the development of the district heating from the perspective of the best available technology of the period. That is essentially what is defining each generation. We have some breakthrough, and then we say, okay, this is sufficiently different from the prior generation, so it's a new one.
Oddgeir, sorry to interrupt you. Would you mind putting your microphone maybe closer to your mouth or speaking up a bit louder?
Is this better?
Yeah, a number of the delegates can't hear you very well, so
Okay.
louder is better.
Let's hope it gets better now.
Good.
So with the different technologies, as we improve them, then we have increased efficiency of the system. And this improved technology, that might be in the pipe network, it might be in the heat source, or it might even be in the heat integration. Then we have a new element, the integration of the energy sector. And then as we move further into the newer generations, it's more potential to integrate the energy sectors. There are more sources available to utilize directly into the system. And we also have more means to support the different sectors. And this then makes the smart energy system. But what we see in the fourth generation, then we also go heavily into renewable energy. We want to exploit that as possible. And all in all, this kind of gives us an idea on how existing system might develop into the future. So it's predicting the development, essentially. Now, how does the fifth generation or the ambient loop fit into the picture? And here the first thing is that we need to agree on the fundamental elements of it. And from my perspective, the unique attribute of the fifth generation, that is the local temperature adjustment at the end user. So it's the heat pumps. And because of we having a heat pump in this building, that then has a ripple effect along the chain. This is then, for example, we might say that we are generating heat at the buildings, so we don't need insulated pipes. We go for uninsulated pipes. Then we might also consider that we have a system with a heat pump, so we want to have a low delta T of the heat source, what is feeding the heat pump. So we have a little bit large pipes as well. And then we have some fluctuations throughout the year or even the day, so we have kind of floating temperature levels as well. And this then begs the question, can we compare the fourth generation with the fifth generation? And here, from the second generation to the third and to the fourth, we are essentially using the same infrastructure and just applying better technologies, different UKDEAs, control logic, increasing temperature, heat sources, and so on. But when it comes to the ambient loops, it's not so obvious. Most likely, we cannot take existing fourth generation system and change them into a fifth generation. It would need a hell of a lot of remaking. And the same goes with the fifth generation. You cannot start a fifth generation and then find out, whoops, we made some kind of a mistake. We should actually dial back and go to the fourth generation. Then we run into a lot of problems. For example, if we have the uninsulated pipes, then sending up 65 degrees in the pipe, that would just ruin the economics. We also have the big pipes will also lead to high losses. And we would furthermore need to change out the end user station, get rid of the heat pump and in with a heat integration. So you can see it's basically a new system that we need to build. And now if we go into a little bit of general comparison of those systems, then yes, they are both based on pipe networks.
Oddgeir, sorry to jump back in again. Is there a fan on in the background where you're sitting? A delicate.
The computer. I'll turn the computer away to leave.
Okay. Yeah. The less background noise, the better, if possible. Delegates are having trouble hearing you. That was all. Lovely.
Yeah.
Thank you.
So once again, I hope we managed to. You managed to hear me now.
A little bit better. The louder you can speak, the better.
So now, if we go to the multi-energy source capability, then there is a difference. In the fourth generation, we are fully capable of using whatever energy sources that are available. And of course, the same applies to the fifth generation, but it has the knack that if we run with a too high quality energy source, we are essentially suffering on the efficiency because we need to run the system with a low temperature so we are not losing most of the heat. When it comes to the load shifting potential, then with thermal storage in the fourth generation, then we can rather easily shift the demand between months or even the seasons. When it comes to the fifth generation, we are always bound on operating the heat pump, and so the load shifting potential is more or less only what we have in the system. And this is then from a few hours to a day. When it comes to the climate friendliness, then in the fourth generation we have a unique opportunity. We can utilize all the low temperature energy sources, and as such we can make a very climate friendly system. But when it comes to the fifth generation, then again we can use the same sources, but we need to upgrade the temperature level when we come to the buildings, and there we need electricity. And depending on the carbon content of the electricity, we can say, we will never get the same results of this. Now, what is commonly mentioned in the fifth generation of ambient loop is the cooling potential. It's a natural part of the ambient loop. We have the heat pump, so it's easy to fulfill that as well. In the fourth generation, no, we don't really have it, at least not yet. We can have it in a symbiosis with the crystal cooling system, but we are also seeing some developments in having a local chillers in the buildings and the ability to use this heating system as a heat sink. So there might be some options coming up. And to the power dependency, then the fifth generation is fully dependent on having a good power supply. In the fourth generation, it's not as relevant. Of course, we need power to pump around the water, but it's a minimal amount of energy that we need. And in the current crisis, then this becomes a quite important aspect. Because what we see, at least in Denmark, where this statistics is coming from, and the green is the natural gas price, that goes through the roof, and the electricity will follow, to a large extent based on natural gas. And the orange one, that is the district heating in Denmark. There we can see the really big benefits of having this traditional district heating with a multi-source heat plant. that it's just stable, and when the power prices go up, we actually get a benefit for the district heating, because then we actually generate some income with CHP plants, and we can subsidize the heat cost. If we move on to the end users, what are the differences when it comes to the end users? And here it's the capital cost. In the first generation, then we have rather simple heat interface units, and they are not so expensive. Compared to the fifth generation, we have a heat pump, and by nature that is more expensive. When it comes to the running costs, then again we have the heat interfaces which are very simple, and they simply last for a very long time, and there's hardly any energy usage of it. So it's a low cost of operating the heat interface unit, and usually we can get quite a cheap heat out of the central heat plants. In the fifth generation, we have again the power. We need to supply power to the unit, and that will eventually or inevitably lead to a little bit higher running cost. Because even though we are paying for the heat in the fourth generation, what we get into the heat interface unit, this will be no different in the fifth generation. We need to regenerate the heat supply, so it can be claimed to be free heat, but actually there is some heat that needs to be put into the system, and we need to pay for that. When we come to user friendliness, then it of course depends a little bit on the business model that is applied. But in a normal situation where the end user owns the heat interface units and then the heat pumps in the fifth generation, then the fourth generation he doesn't need to do anything at all. The system just runs more or less. But if the end user owns the heat pump, then there is more to it. There is more service that is needed and so forth. And then it comes to the business model. That, of course, the utility can own and operate the heat pump and take care of everything and just sells the heat to the end user. And then it's a similar level. So where might we see those different systems? Not in middle of London for sure, based on what we heard. Then we will only see traditional district heating or heat networks, fourth generation, maybe third generation. But for the fifth generation, it's not very clear to me where they have their advantage. So it's a little bit case specific. Where I can imagine is that where we have quite distributed buildings, so long distances between the different buildings, and not too many of them. We are not able to get the economy of scale into play. Then we can look on some wider considerations, and this also is favoring the fourth generation. The dwelling noise is lower. The current industry skills, it's very high. We have this heating in many places, and we have a lot of experience from that. And because of that, then there is a low risk towards the utility. There's also low commissioning risk, and compared to the fifth generation, we are basically opposite on those. When it comes to the operating data that is available, and we have been running the traditional district heating system for 100 years plus. So we have a lot of data on that, and this is not the same for the fifth generation. For reliability, robustness, and system resilience, then this is a lot about that we have multi-sources in one system supplying already directly usable heat in the fourth generation. So there we can switch between different sources and create a lot of resilience. In the fifth generation, it is the power dependency that will make a little bit of a tough situation. So I will end with this slide showing what we, or I at least, see as the future vision for district density, and this is a half moon where we have the generations of district heating coming to the top, and then generation of district cooling. And there we meet at the end where we have the optimal system for supplying heating and cooling. In the fifth generation, I see more in the outer in rural areas or where we have only limited amount of buildings. So thank you, and I leave the floor to you, Simon.
Lovely. Thanks very much indeed, Oddgeir. Thank you for being with us. When you come back to the Q&A session at the end, there's certainly a lot of questions in the chat. You can kind of fiddle with the noise in the background. That we really appreciate it. Thank you very much indeed. Okay,
Good, thank you.
I'll ask you to leave the stage now, and Tom, if we can drop down Oddgeir's slides and put up Joseph's slides. So I'd like to invite Joseph and Tom Sophie to come onto the stage with me. And Joseph will be talking about design comparisons of fourth generation district heating networks and ambient temperature networks using console heat. So Joseph, do you just want to start and I'll just check I can hear you okay?
Yeah, can you hear me?
Yeah, I can hear you okay. Thanks very much indeed.
Okay, thank you. So I will kickstart with what Oddgeir was talking about, the differences between fourth generation and fifth generation systems. Just to reiterate, the fourth generation systems, we have a low temperature source with the network temperature levels of 50 to 70 degrees Celsius. So we require minimum source temperature to supply to space heating and domestic hot water demand, since we don't have any building side source equipments. That's for the fourth generation systems. And if you look ambient loop systems or the fifth generation systems, we can go to ultra low temperature source with the network temperature levels between 10 degree to 25 degree Celsius. So we have vast range of source availability. We can use rivers, lakes, sewage water, data centers, and so on. But then the problem is we only have 10 to 25 degrees Celsius, so which is not enough to heat the buildings directly. So we need heat pumps or any building side source equipments which are necessary in the fifth generation systems. And about the fifth generation systems, we can go for both heating and cooling. So if you look into the fifth generation systems, in this case, so we have a source in this case, and then since the source is very low at 5 degrees Celsius, so we have a centralized heat pump which pumps from 5 to 15 degrees Celsius, and then we have a heating mode, which means you have heat pumps at each and every building, so distributed heat pumps. And then the supply pipe supplies low temperature, ultra low temperature water here, and then it heats the building and it returns the cold water back to the source. It can also be in the cooling mode. So we can also use the distributed heat pumps in the buildings to cool the buildings, and then it returns the hot water back to the source. So in fifth generation systems, we have both heating and cooling mode. So, but in this presentation, I'm going to focus mainly on heating. I'm not going to touch into cooling. So then, so we did a study, the case study, to compare maybe the cost aspects of fourth and fifth generation systems. So how much cost does it require to build an ambient temperature network? So would it be better economically cost-wise when we compare with the fourth generation system, how the cost changes between fourth and fifth generation systems? So we did a case study in Glasgow city center. So with the area of 1,340 buildings. So it's considered with a yearly heat demand of about 140 gigawatt hour, the area in the Glasgow city center, these buildings. And then we separated into 4 different clusters of this particular building. And there is a river Clyde going over here. So we estimated the peak capacity from the river Clyde about 250 megawatt thermal. And then the energy capacity is able to supply about 2,000 gigawatt hour annually. So the river source can be used to heat these buildings. And then we also need a heat demand of the building. So in order to estimate the heat demand of the buildings, so we used open source project, which is hot maps. So where they project heat demand density data and gross floor area density data for all over Europe. So we use this open source data to calculate the heat demand of this building. So I will explain with this case study what we did with the fourth generation design and also with the fifth generation design, and the cost aspects, how the cost compares the investment cost and the operation cost between these two designs. So then I used ComSoft Heat to do the designs of 4th and 5th generation systems. So what is ComSoft Heat? So the software has the ability to calculate the designs of different 4th, 5th generation with different features, and it will give you the investment cost and the investment analysis. So we require GIS data and energy data as an input to the software, and then we also need to some technical parameters in here. So we can provide 4th generation or the 5th generation inputs, what kind of network, what are the supply return temperatures, and so on. And of course, we need to provide a proper unit cost. So what are the cost assumption we made? So in this case study, we also made quite a lot of cost assumption to compare these systems. So those needs to be right to have a proper conclusion. And also we have financial data that needs to be put in, and then the software will provide you the network topology automatically, which streets to take, and the 5 dimensions, how big the part should be, the capital cost, and the investment analysis. So first, I'm going to look into the 4th generation network design. So as I mentioned, we have 4 different clusters in this area. So we provided with centralized heat pump of each of these clusters. So each cluster is provided with a centralized heat pump, which is used to supply heat to 70 degrees Celsius. And then the network supplies heat to this particular cluster. So then if you look into the network parameters, so we used steel pipes. We configured steel pipes in the software, and then we use 10 bar pressure with the supply and return temperature of 70-40 in this network. And then it turns out to be we require 73 kilometers of network in this particular area. And then we used the heat pump investment cost of 1 million pounds per megawatt. But then it also includes the heat pumps and the infrastructure to develop the energy centers and the electricity grid and so on. So all included, it's 1 million pounds per megawatt. That's what we use for this study. And then the circulation pump cost of about 50,000 pounds per megawatt. So if you look into the design, we did the design in the software, and then with the pipe networks and so on. So this is the 4th generation design. And then we also did the same area. We also did the 5th generation design. So 5th generation design, which means, okay, we took the water from the river and we put the centralized heat pump there as well. But then it pumps the temperature from 5 degrees Celsius to 15 degrees Celsius. And then the ultra low temperature network that supplies 15 degrees Celsius to each and every house. And then we have distributed heat pumps at each and every buildings that pumps further the temperature from 15 to 70 to supply heat to the building. And then it returns 5 degrees Celsius back to the source. So here in the 5th generation system, so we have plastic pipes at 6 bar pressure, and then we have supply and return temperature of 15 at 5 degrees Celsius. And then for the distributed heat pump, we used 400 pounds per kilowatt. That's the cost we used for the distributed heat pumps. So now let's compare the design scenarios. So first we have the 4th generation design, and then in the 5th generation design of the Ambient Loop Networks, we provided the COP for the heat pump, the simulations with 2.5 of COP and 3.5 of COP. So in that case, if we compare these 3 designs, so we have a peak heat demand of about, without simultaneity, of about 78 megawatt. So if we consider simultaneity, it turns out to be 48.8 megawatt is required for the 4th generation design. And then for the 5th generation, the thermal heat is 29.28 megawatt, and then the 19.52 required electricity for this particular case. And then for the case with the COP of 3.5, we require about 35 megawatt peak, and then the electricity of about 14 megawatt. Of course, if you look at the pipe diameter, so the largest pipe diameter is DN300 for 4G design, but then we have DN450 for the 5th generation design. That's because we have very low temperature difference for the 5th generation systems when compared to the 4th generation design. So now let's compare the cost, how the cost pans out between these scenarios. So if you look into the 4th generation systems, we have source cost here, which is in the blue, and then we have distribution network cost, and then we have heat exchangers in the building cost. These are the 4th generation cost. And then if you look into the 5th generation cost, the source cost is a bit lower because we require lesser thermal energy. And then the distributed heat pump cost is taken into account in the demand side. So we require higher cost in the demand side. And then the network cost is a little bit lesser because we use plastic pipes for the fifth generation systems, and the fourth generation system we use steel pipes. But of course, trenching cost is the more dominant cost, but then we slightly reduce because of the lesser pipe cost for the plastic pipes. But then the investment cost, seems to be at the same level if you compare. It depends on the cost assumption you make, but there is no much difference in the investment cost. But of course, we did not take into account the replacement cost of the heat pumps, because the heat pump lifetime, the distributed heat pumps lifetimes are much lesser, 18 to 20 years, when compared with the heat exchangers. So then if you compare the operational cost, so the fourth generation operation cost is much lesser when compared with the fifth generation networks. The reason is because the COP is higher, and also we can get cheaper electricity using a private wire for the centralized heat pumps. But then for the fifth generation distributed heat pumps, we still require electricity from the grid cost, and the electricity cost is much higher. So if you compare the total cost, then the fifth generation system cost will be much higher when compared with the fourth generation systems. But then in the investment cost, initially we said we need a heat pump here because we only had the temperature of 5 degrees Celsius. So we had both centralized heat pumps and also the distributed heat pumps. In case if you have already a free waste heat source which is available at 15 degrees Celsius, then we don't need the centralized heat pump. We can directly use the 15 degrees Celsius to supply, and then we can only need distributed heat pumps. So if you analyze this scenario, would it be better cost-wise if we take this approach? If you assume we have a free heat source at 15 degrees Celsius, if you eliminate the requirement of centralized heat pumps, so then in that case, the investment cost will be lesser because the source cost is much lesser in this case. But then if you look into the operating cost will be still higher for the fifth generation systems because we still have higher electricity cost and lesser COP when compared with the fourth generation systems. So the total cost in this scenario is still higher for the fifth generation systems, even though it's getting closer, but still we have higher cost for the fifth generation systems. So, and also if you also compare, but this case is not realistic, but just to get a sense, if you're going to get a same electricity price for the centralized heat pumps at the big central private wire, and also for the grid cost of the each and individual consumer with the same electricity price, even if you do with the same electricity price for both of these scenarios, still fifth generation systems seems to be on the higher side, even though for the 3.5 COP, that's not a very good realistic case, but still the cost seems to be on the higher side, and then the fourth generation system seems to be good. But of course, I did not consider cooling, so I only considered the heating aspects. So to conclude, the total cost is much lower for the fourth generation systems when compared with the fifth generation systems. If we also require centralized source and the high and the expensive electricity cost. But then the fifth generation system might be suitable financially if you find a free low waste heat source available. So in that case, that makes sense. But then if you are getting a free source at a higher temperature of 50, 60 degrees for the fourth generation systems, but then still fourth generation systems might be better off when you are comparing with the fifth generation systems. And the fourth generation systems will have higher heat loss, of course, because it's operating at a higher temperatures. The fifth generation systems can have low heat losses. But then fifth generation systems will be interesting where we have simultaneous heating and cooling loads which are present, because we are in this study we only looked into the heating aspects. But if you look into areas where we have simultaneous heating and cooling loads which are present, then fifth generation systems might be interesting financially as well in that case. And also if you want to exchange energy between heating and cooling. So if you look into that point of view, fifth generation systems might be interesting. But if you only look into either heating or cooling, so in that case, with the cost assumption we made and the study we made, it seems to be fourth generation systems seems to be at a good financial situation when compared with the fifth generation systems. So yeah, that's all my presentation. And if you have any questions, yeah, please put me in the chat. Thank you.
Brilliant. Thanks very much indeed, Joseph, and much appreciated for you keeping to time. Very interesting presentation. It's generated lots of questions in the question session, so if you want to pop over there, I'm sure you're very welcome to read those and start answering them. So if I could ask Joseph to leave the stage and for Asad to come on. Morning, Asad. Asad has kindly stepped into the breach to talk about sustainable heat, consideration when comparing fourth to fifth generation and ensuring a sustainable solution. So do you want to kick off, Asad, and I'll check your sound's working okay?
Yeah, morning, Simon. Morning, all. Is this coming across okay?
Absolutely perfect. Thanks, Asad.
Brilliant. Okay, so I'll be talking about fourth and fifth generation in the context of sustainable heat. So what exactly is sustainable heat? It's essentially the provision of thermal energy that achieves the balance of economics, environment, and social requirements over the lifespan of the project. So that's not just the upfront capex; it's the whole life cost. And when we consider that, a sustainable heating solution for one project may not be the same solution that's appropriate for another. So it's very much a project by project thing. So what the three pillars are, you've seen this before. It's economics, environment, and social, and we can't assess what a suitable heating system is for a particular application without considering all three of these, and each project is going to have its own focus. And these factors need to be captured as real KPIs, key performance indicators, and tracked throughout the lifetime of the project, that it extends really into its operation. And we've got some KPIs that would be typical of a heat supply, but it's going to be unique to each project as well as the value and the weighting of each one. So similar to Joseph, so I won't go into the particular aspects in too much detail, but when we think about a new build, high density development in a city development, let's say 200 residential units, we've got a decision to make on what system we'd look to install. And from a generation perspective, we're going to go with an all-electric solution, and we've got an option of fourth or fifth generation. Now, in terms of the generation plant, fourth, we would look at an air source heat pump providing water at 60 degrees, and in a fifth gen solution, in the absence of a heat network or a ground loop, so quite a typical scenario in an inner city development or plot, is an air source heat pump being mounted on the roof of that unit. And then on the distribution, like been introduced, the fourth generation has the option for steel and a 30 delta. Fifth generation having a plastic system. Just noticed I hadn't flicked slide there, so catching up. And then delivery, you've got a fourth gen having a passive instantaneous plate heat exchanger at that building level, whereas a fifth generation has the active heat pump providing space heating and stored hot water. So that's really the key differential at the dwelling level. And then really for the customer, what we want for them is to not really notice what kind of heating system they've got. Both should be providing the same level of performance. Of course, the difference is with the 5th gen, you're likely to have a stored hot water cylinder to both reduce the capacity of the heat pump within the dwelling and to offer some buffering and sort of run on for that heat pump unit, whereas the 4th gen HRU is very much instantaneous. So comparing the two systems, assuming that you've got an average flat, it's got 3,500 kilowatt hours a year, we're just assessing really the energy performance. So purely the kind of the energy balance in these two systems. So using an hourly model of the predicted performance, the 4th gen air source heat pump system is slightly worse as a kind of COP perspective. Obviously has to lift water temperature from 30-60 all year round. The 5th gen system slightly better as it only has to do the 6 to kind of 25 degree lift. And then the 4th generation, we've assumed here to have a kind of industry minimum performance in terms of heat loss, aligned with CP1, whilst the 5th gen system, the heat loss we're considering negligible for the purpose of this analysis, given it's running close to ambient temperature. At the customer energy, a key difference in the 4th and 5th gen is the need for the additional energy needed by the customer to run that dwelling level heat pump. So you've got that water to water heat pump, and that energy is provided by the customer. And then the customer interface heat loss, you've got losses from the HRU, and you've also got slightly more losses from the hot water cylinder in the 5th generation scenario. So on balance, they're close to the energy input for both scenarios, and there's really not a lot between them in this level of assessment. So I haven't looked at the embodied carbon assessment for this, but we'd reckon that 4th gen would also outperform a 5th generation system, mainly due to the slightly smaller pipe work. You've got mechanical HRUs instead of the number of water to water heat pumps and the kind of equipment that goes alongside that. So quite a useful document, certainly recommended reading is the CIBSE AM16, and this one really stresses the need to include that residential electrical power in calculations when assessing a 5th gen system. So quite often one of the heat pumps will get missed out because it will be, oh well, that's provided by the that's powered by the residents, that's covered by their bills, and it just skews the whole analysis. You really need to be considering the electrical input into both of the heat pumps to get a reasonable like for like comparison. So going a little bit into the cost performance, the economics, and kind of strong caveats around these numbers. They're not going to be reflective of all projects and kind of commercial models, but these are sort of typical values taken for this comparison. From a capex perspective, and a kind of theme from the earlier presenters is that the 4th generation is cheaper per dwelling than the 5th, and somewhat from the kind of pipework risers being more expensive in the 5th generation, and of course the interface, that HOU. We've taken the for the purposes of this, the OPEX as being equal across both scenarios. Arguably, you've got a bit more to maintain in a 5th generation scenario, so that could be a little bit higher. And then the costs have been split into a landlord heat and a customer heat. So the tariffs we've based here are based on a break-even position in kind of 20 years of operation. And you may balk at these numbers, but they're based around a current June 22 electricity rate that's been negotiated. So that's kind of somewhat reflective of the current electricity market, and that's including variable and standing, just to kind of give us a comparative number. And then customer electricity, so the 5th gen obviously requires electricity to be used in the dwelling to lift the ambient system to usable levels. At the June 22 capped rates, this values has been based on, so that to stress is the residential rates tariffs being capped based on, it's actually April's price cap being put into place. That's obviously suspected to change in October. So then going into total cost, in this simplified scenario that we've set out, the cost of heat actually is slightly smaller for the 4th generation system, and somewhat due to the unusual electricity market or energy market that we're currently in, and on the basis that the landlord procured electricity is not protected by the price cap. They're paying the market, the commercial rates. Therefore, the cost to the landlord is higher, leading to a higher heat tariff in the 4th generation system. But very much a unique position that we're at the moment. So just to kind of draw that out a little bit, we've been looking at this analysis with 3 different scenarios of electricity tariff. So what I presented in the earlier slide is currently the June 22 numbers. Like I said, slightly cheaper for the 4th generation. But if we say go forward to October, and the price cap results in speculatively a price parity between commercial and residential. So I hope it doesn't go up this much, but both the residents and commercial are paying a 42 pence per kilowatt hour for their electricity. Then the favour sort of shifts slightly more in favour of the 4th gen actually in this scenario. And then if we go back to historically, say April 19, where the residential electricity is what we typically see as being more expensive than commercial. This impacts both the landlord cost of the 4th and the 5th generation system. So heat tariff reduction, as well as the customer costs arising from the water to water heat pump. And actually in that scenario, we see even more of a drift between the 2 systems. So I mean, none of these costs are intended to be predictive of the cost seen by the dwelling occupant, but they're just indicative of the kind of relative performance and selection of the procurement and the operating model of both of the heating systems and dwellings themselves is going to be one of the largest factors in assessing the financial performance, and these different approaches haven't been shown, just because you go down any number of those. So just to go forwards, does this mean that we're saying that fifth generation doesn't work? We're not. But so it's not the incorrect choice for all projects. Certainly not. Based on the current sort of market trends, fifth generation is outperformed by fifth generation in a heating only new build application. So to stress that point, existing buildings fare worse than new build, but enhanced building performance, such as passive house, might change this analysis. And of course, like some of the other presenters have introduced, fifth gen can of course work very well where there is heating and cooling is required local to one another. So what do we need to do to assess the correct solution for the project? It's very much to identify the project KPIs. If the client doesn't identify them, then the consultant and design team should really be driving this discussion. We don't want projects where the capex is prioritized at the detriment of the end user, the tariff to the resident. And always consider which option provides the best value. Again, never focusing on just capex, and always identifying the best whole life cost. So this approach really requires a bit of a step change, especially at kind of the early energy strategy level, and alleviating part of that risk is using the CP1 process to ensure the heat network is developed to a known and communicated standard of performance, and that whole life cost is really bedded in to that approach. And just to stress that the engineering is important, but the commercial approach and the financial value of the heat network as the asset can't really be overstated. And advice should be kind of sought soon as possible in a project to help move the heat network from what could be a static liability to really a dynamic asset. So thank you. That is me done.
Thanks very much indeed, Asad. That was a very interesting presentation, much appreciated, and interesting to see some more numbers comparing the two different options. So thanks again. So lots of questions in the chat. So Tom, if you can pull down the slides, that'd be great. And we'll invite Matthew King to join us on the stage, and for Matthew to present his opportunities and design considerations for fifth generation network. So Matthew, shall I allow you just to kick off for a second, and I'll just confirm your sound's okay.
Hello there, can you hear me okay?
Perfect, lovely, thank you.
Thank you, Simon. So my name's Matthew King, I'm an Associate Director at Hilson Moran. We've completed a number of projects looking at both fourth and fifth generation, and have gone on to design a number of fifth generation networks. I think Asad and Joseph and others have done a very good job in discussing the differences, but I'm going to keep my presentation quite high level and maybe look more to the future and some more pointed points. So I'll start my slide. So I'm going to talk about the applications of fifth generation networks. I think it's quite clear from the previous presentations that it's very much based on if it's a high density development with cooling and waste heat opportunities, rather than just heat dominant applications. So I'll go through that, and opportunities for low carbon energy sources, and then the commercial impacts and opportunities for the network operators, and then look to the future and actually how this sort of goes into the net zero targets and for 2050. So one key initial point I wanted to make is the difference between the two is this thermal inertia. You have local storage, domestic water storage, which is quite key, and it does offer the opportunity to reduce overall electrical supply power to the developments, and this is very much caveated with your scale. So a couple of projects we've done when we were looking at the out-and-out winner of the comparison on CapEx and OpEx costs on fourth and fifth would have been a fourth generation because it was heating dominant. When you look at some of the maybe more project-specific or development-specific constraints, so reinforcement costs on the electrical grid and other things, there may be marginal costs that shift it the other way. So a Canning Town project we've recently completed, the reinforcement costs on the UKPN grid were significantly high, and the difference between the two networks enabled us to reduce costs on that, and it actually tipped the balance slightly. The other key consideration for also that project and others is the central plant size. So integrating the energy centre, which are normally incentivized to be one large energy centre, certainly in a London GLA development, into the schemes and initial phases, it can offer benefits for the developer and also reduce cost in terms of the whole project. So a fifth generation network, you can reduce your central plant size, obviously, and have other opportunities of maybe integrating that with areas like roof plant and other spaces that you wouldn't often use or need additional space for that. So that's quite a key point in terms of applications, not just to do with opportunities of waste heat and cooling led or more cooling or balanced networks. There is some other things to consider there. Another project example where we were sort of considering a fourth generation and then looking at the fifth generation comparison, it was very project specific, is the opportunity for more low carbon energy sources centrally. So we were exploring opportunities of ground source that maybe we couldn't fit enough in the site, and that fifth generation would have just needed that without supplementary central plant. So it is worth considering that on your projects. So the other element of waste heat, so the fifth generation network has a great opportunity to utilize very low temperature energy sources, and there's a lot of them in an urban environment, and this is sort of an example, so data centers and other environments. The fourth generation obviously is a higher grade energy center on distribution, but with suitably designed water to water heat pumps can utilize these also, but they require a higher supplementary energy input because they're lower COP when doing that. So I would say that fourth generations are slightly better suited to heat pump technology, but that looking at the round and obviously the previous presentations, that is very project specific. The other key consideration when looking at a fifth generation network to harness the opportunity of waste heat and free or low carbon energy sources is thermal storage. So it's key for fourth generations, but even more key for fifth generation energy networks. The other key point is in urban environments is the cooling demand, which I'll go on to. So the commercial opportunities. So when you're looking at a fifth generation energy network, your primary energy plant size is normally at about 50%. So when you're thinking about in terms of an ESCO and network operator, you're only providing 50% of the heat compared to a fifth generation. So your revenue is reduced, and that can look pretty negative commercially. But you've got to look at the fifth generation design, if designed correctly, at the other opportunities of capturing revenue from other sources, so commercial adjacent development, so retail and other commercial offerings that are wasting heat into your network, and then you're able to sell it on. So you've got to consider yourself, rather than an energy generator, maybe an energy exporter, and you won't often be generating as much energy as a fourth generation, but you will be potentially harnessing two levels of revenue. So looking at a retail unit, a small scale retail unit, they're conventionally using heat pumps, so DX or split units for heating and cooling, and their cooling sort of COPs are around 4 or so. So their cost per kilowatt based on a 20p per kilowatt hour is about 5p. So looking at the revenue opportunity there, you're able to charge them slightly less because then you're then charging residential units and so on, and other customers for using that heat to generate domestic hot water in summer, or both space heating if there's a simultaneous heating and cooling demand. So looking at the economics there is quite an important start to the 5th generation, and it can be almost comparable when you're thinking about that. So that's just in an operational sense. Then your important point to harness these opportunities, it's very important to provide energy metering at all sources of heat and energy uses from your network. So the split between the residential input energy and the central heat is important. So that's just a more of a point to highlight really in the design and consideration of energy networks, 5th generation. And I think Asad made a highlight of this earlier. The relatively high waste heat loss of the 5th generation network was one consideration we had early on when looking at this. The aspect of this is that it's after the meter, so there's a lot of standing losses in the domestic hot water storage vessels, and that can exacerbate things like internal overheating in residential units and so on. So that's a key consideration. But also commercially, compared to a 4th generation network, you're not losing it from your side of the meter. So that isn't your cost as an ESCO on a network operator, it's after the meter. So it de-risks that slightly, but it is a significant cost to be considered when looking at these network designs. One thing looking at the future, and I think we're sort of very sort of short-sighted in our current sort of net zero and carbon emissions appraisals of these systems. I would say that a problem we're going to have, especially with climate change, this may not be the short term, this may be the medium to long term, when we're designing energy networks that will be in the ground and operational for longer than 15 or 20 or more years, is the fact that social mobility and economics of residential units and so on in high density urban environments, they will look to retrofit cooling. Retrofitting cooling in addition to a 4th generation network is obviously very costly and disruptive and quite difficult in development. Riser space and other restrictions are a problem. Fourth generation networks can't obviously cater for that reversible heat pump operation locally to residential units. So the opportunity in the future, and it's not currently something that I think the GLA and government are really considering, in my opinion, but if you're looking at 5th generations and that whole life carbon, maybe this is something we should consider as well. The loss of multiple DX systems and other retrofit systems, or more costly in terms of carbon, distributed cooling strategies. You're able to capture that heat, not exhaust that into the atmosphere, and utilize that in your 5th generation network. And that's a future-proof scenario of 5th generation network, which I think I'd like to highlight to maybe being an opportunity in the future to work towards the net zero targets in 2050. That does often require retrofitting different local heat pumps in the apartments. So there is maybe a medium-term change to the end of life of your local heat pump, which is typically 15 years. You'll be looking to put a reversible type, and then you've got to obviously overcome the technical issues of getting that cooling into the apartment, either via cooling the MVHR, fan cool units, or I'd like to think in the future we can look at higher chilled water temperature underfloor heating systems with better controls so we avoid condensation. So that's something that's developing, and it may be something that maybe be addressed in regulation and policy later on. But 5th generations is certainly future-proof. And there's a win-win scenario in that in doing this as well. So we're capturing the heat that would normally be exhausted to the environment. We're putting it back into the energy network, offsetting the primary or central plant operation. And although urban heat island isn't something that's normally associated with air conditioning, it's normally predominantly through surfaces and the lack of vegetation in urban environments. It is also exacerbated, or there is a contribution to it because of air conditioning kicking out waste heat during peak summer periods. So there's a lot, sort of a diagram demonstrating that, but it will help reduce that problem and then help in our net zero route. So customers, so we talked about cost to customers and the comparison earlier on, And I think it was very much a single-use scenario. So I think I'd like to just maybe open up to the Q&A session that when we've assessed domestic hot water consumption, we generally look at different consumption profiles, so low, medium and high. And often we find the 5th generation is more economic when looking at higher domestic hot water uses in residential dwellings. A contradiction to that is they generally these higher domestic water profile uses are in high-end residential, and I think that is something that we're struggling to sell the local heat pump operation, because I think it requires a behaviour change when utilising this. There's very different operation profile for these types of systems. So your instantaneous 4th generation system is instantaneous hot water straight away and continuous. Your local heat pump for a 5th generation network is based on a storage volume that can, depending on the use and demand, can run out, and then you have a high recharge period of maybe up to 2 hours, depending on the system design, which in high-end residential isn't often acceptable and can be problematic. But going on to the benefits of 5th generation networks for residents, I think we've talked about the application where it's suitable for, which is where you have a waste heat or a low carbon heat demand, which often means lower prices of generation or exporting that at a lower price to the residents. So they have a variable tariff, and that is, it's all possible with the metering system. That gives us energy security for the residents compared to a 4th generation network in the future. So the current sort of situation at the moment, a 5th generation may fare better if you have low carbon heat sources, so you're not as reliant on electrical energy and the cost of it in the future. And I'd like to think that obviously the electrical energy charges will go down as they stop subsidising fossil fuel based primary energy. But it's just a key point there that I think there is a consideration with profile of domestic water use. So in summary, and it's quite a brief one, I think a lot was said in the previous presentations, and I think I'll probably allow more time for the Q&A because this is really topical and there's a lot to discuss. But the 5th generation networks are more suitable to mixed-use developments where there is opportunity to harness low-cost or low-carbon heat. Waste heat recovery is the key element to make it viable, and that unless you're considering restrictions or constraints on sites where you have massive reinforcement costs, or you just haven't got the areas to accommodate a 4th generation energy centre. The other thing is the opportunity to future-proof our trajectory to net zero, and that is probably the end note really there. So I welcome questions on that.
Brilliant.
So,
Indeed, Matthew, much appreciated. If I can invite the other speakers to come back to the stage, please. So Oddgeir, Joseph and Asad will move on to the Q&A session. Asad, yep, that's great. A number of questions for yourself. So lots of questions. I think this has been one of our most controversial seminars that we've done, which is good because it's always good to get a bit of chat in the room. So if we can, if you can see the questions in the question session, I've scrolled right to the very bottom to be fair to the speakers. So Rene Verhoeven has asked a question: uninsulated pipes will result in quite high heat cold losses, even if medium temperatures are close to ambient, which they're not. What's your view on this? So do any of the speakers have a view on the uninsulated pipes? If medium temperatures are close to ambient. Anybody would like to pick that one up at all?
I think one of the benefits, sorry, just jumping in there, that we have developing these systems as well to developers is not having issues with overheating in corridors. There is a negligible loss because your distribution temperatures are so close to your ambient that insulating them, and you do have to worry about condensation in certain scenarios. So if you're taking a lot of heat from the network, if you've got that in exposed environments, you can have situations where you're getting to dew points. So you might need to consider plastic pipe work that offers a level of insulation, or cast iron or something with a negligible level of thermal insulation just to deal with condensation. So you have to design the system and consider insulation even on a 5th generation network.
Okay, good. Thanks very much. Anybody else, or should we move on to the next question?
Yeah, I think if you're looking at the energy center to a building level, so a kind of a district-wide network, then obviously the pipeworks in the ground, your deltas between the ground temperature, say 10 and 20 compared to 10 degrees and 60 or 70, but it needs to be assessed on a project by project basis whether you need insulation depending on how far you're transmitting that heat. Ambient loop pipework also typically going to be a much larger diameter, as Joseph introduced, so increased chance of losses there. So insulation may be required. It might be series 1 or less, certainly a lot less than you'd expect with steel.
Okay, cool. Thanks very much. Ian Goodchild's question above, which is a common theme amongst a number of the questions. So there's talk about running costs on 5G higher than 4G for the end user. Do any of the speakers want to talk about what cost they would expect the end user to pick up? I'm thinking about the fact they'll clearly be picking up the electricity cost for running the in-dwelling water-to-water source heat pump, but also in terms of the maintenance costs and the capital replacement cost as well. Have any of the speakers been involved in setting tariffs that a customer will pay, not with an ESCO scheme, but in a cost recovery or a cost recovery scheme for any kind of developer at all? Has any of the speakers been involved in that?
So I can jump in on the maintenance costs. I think the previous projects we worked out haven't been the operating costs of primary energy, so haven't been based on the more recent hikes. This was a year ago, so they might be a bit out of date. So I welcome the other speakers to comment on that. But in terms of maintenance costs, when looking at that compared to a 4th generation, I think there was a slide on it earlier. I think Asad put £150, and I think that was across both networks. When looking at it with the manufacturers of the local heat pumps, they offer, if it's a residential owned and maintained local heat pump, they offer equivalents to your sort of monthly costs of £20 or £30, so £200 a month. £200 a year in terms of maintenance costs, and that would also sometimes involve things like maintenance of MVHRs for free as well. So working the likes of Dimplex and Dakin and so on, they offer these packages. When you look at that, when it's owned, when the local heat pump is owned or operated by the building company or ESCO, they can offer more competitive rates because of scale and so on. So there is a negotiation or contract on there. And I think we mentioned it earlier. I think the skills shortage for maintenance and so on, it has to be addressed when we develop more of these, especially also the 4th generation with the central plant. But the local heat pumps, when we're talking to manufacturers and operators, they are scaling up and they are trying to skill and train FM and maintenance companies. So I think it's hopefully a short-term issue, and we will quickly change and have a more readily available man in a van to fix these things. And when they're looking at maintenance, I think it's quite important the type of maintenance. So the heat pump sections are hermetically sealed units, so they have to go around with spare units that quickly are interchanged because of quick connections into these units as well. But other conventional parts are available on the market. Conventional now, it's the heat pump section, which is more of an issue when we're looking at aftercare and cost. The other key consideration when we were looking at whole operational costs, so replacement as well, it was equivalent to a 4th generation network of a 350 unit size. So the cost of replacing all the units at the end of life didn't make a big difference. There was a slight difference between them. I'd have to dig out the cost, but it wasn't as drastic as you might imagine.
Okay. All right. No, thanks very much. That's a full answer. Any of the other speakers wish to chip in, or shall we go on to the next point?
I think Matthew covered most of it. One thing I would add is ensuring that in the ambient system, the ambient heat is being metered fairly to residents. that there's been systems in the past that have got away with just a kind of a flat standing charge across all residents for that ambient heat, and then they're just paying for that electricity. So whether it is that communal air source heat pump, its operation being split prorated against the operating of each of the individual heat pumps, or it's actually installing meters on that loop, that needs to be considered in the system design.
Okay, no, very important point. Thanks, Asad. Moving on to Mark Nichols' question. I appreciate Oddgeir's already responded, and that was sort of a question to him, but and I kind of agree that it's a case-specific basis. I don't know whether any of the speakers have had experience about comparing 4th gen to 5th gen networks in terms of embodied carbon, operational carbon, whole life carbon, and whether anybody would like to comment on that, or should we leave it with Oddgeir's response?
I think it's a tough one, Simon.
I think it's a scheme-specific response. We'll leave Oddgeir's response.
I would sort of open up the question to the industry, really, that we need to be looking at embodied carbon for all the decisions we're making in terms of whether we're going 4th or 5th and other plant selections. But yeah, it's a key consideration, and it's a very new sort of assessment we're doing on these things, but I think it's important. And as I said earlier, you need to maybe look at the potential to save in terms of build and the energy centre sizes, because there is embodied carbon in those when you're comparing the two, but also the offsetting the local cooling systems, maybe if you're looking at 5th gen, which I mentioned earlier. So it's quite a complicated calculation. It's very project specific, and unfortunately there isn't much data out there on a lot of the equipment. But if you look at refrigerant and the volumes of refrigerant between the two systems, there are lower global warming potential refrigerants for local heat pumps now with the Dakin Altherma on an R32 type refrigerant. But the other type refrigerants from other manufacturers are 410A based, which has a higher global warming potential. You need to consider the volumes of refrigerant in that calculation as well, which is often forgotten.
Okay, right. Thanks very much.
And it's also, I hope the sound is better now.
Yes, it's a lot better.
Seem to have been a victim to technology. But I think it's also important to realize that the losses of refrigerant in a central large plant is lower than what we would experience in smaller heat pumps. That's just a fact.
Okay, sure. Thanks very much. And moving up, Oddgeir, there were some questions about what one of a kind means in terms of user friendliness. I'm not sure that we need to focus on that, but maybe you could respond after the event, and we'll cover that. Do you believe, there is a question from Rene Verhoeven, another one from Rene. His perception is that your analysis of 4G versus 5G is based specifically on the Nordic situation. Do you believe that, I mean, certainly the other speakers, Asad and Joseph, and seem to indicate that the analysis is not specific to the Nordics, but do you think there's anything particular happening in Denmark that isn't the same as in the UK, and that your analysis should also apply to the UK?
There is not a big difference between the UK and Denmark, and as such it should definitely be valid, but the issue is always with the cooling dimension. So how that is coming in, if we believe that the residential will demand cooling in the next few decades, then we need to consider it, of course. But if it's mainly commercial cooling that we are expecting, or in a very high-rise buildings and so on, where it's rather concentrated, then it simply might be much more efficient to have a cooling grid as well, even though you have double set of pipes. I mean,
Sure. No, very important. This other speakers brought out as well. I'm conscious there were some questions for Joseph, but he kindly answered those in the chat, so I'll skip through those questions that he's already answered and try and move up some of the more later ones. So one you haven't answered, Joseph, is from Asad Kwaja. Sorry if I've put your name wrong. Question for Joseph. It's the one you've responded to above, Tejapal. So it's how sensitive the results are to the assumption that we need 70 degrees C for buildings. Any thoughts on that particular one, Joseph?
Yeah. So we did the simulations for 70 degrees Celsius because if you look into the actual buildings now, if you look at, for example, the case we discussed with Glasgow, so most of them are old buildings and that require at least 70 degrees Celsius to heat up the buildings, or we need to do thorough renovation or energy efficient measures to bring down the temperatures down to 60, 50, or even more down. So we require at least 70 degrees Celsius to heat the building if you look into the current situation now. So that's why we focus on the 70 degrees Celsius. And of course, if the temperatures are varying a bit, and if you have more energy efficient buildings in the area, and then that might lead to good case for food generation systems. We can have like different temperatures with the different buildings. But we focused on the current situation now. That's mainly we need the renovation is required.
Okay, no, that's thank you for that answer, Joseph. There's a question above from Simon, but I think hopefully that's been covered in Asad's presentation. I don't know whether you want to talk any more about that, Asad. So it's looking at whether the fifth gen not lock the resident into high price electricity for the life of the building and increase the chance of fuel poverty. I know you did a bit of analysis on looking at what the total costs were and the savings, fourth gen, fifth gen. Did you want to speak any more on that particular point, Asad?
I mean, obviously there is a risk that with the customer having to pay for that power compared to, say, an ESCO tariff, which would probably absorb to an extent some increases in the pricing, but it's going to be very project specific scenario. So not much more to add on that.
Okay, no, that's fine.
I just wanted to add, I think the point earlier is if the fifth generation network has a lower cost energy source, so waste heat or cooling, that does open up the opportunity to reduce the central plant size, which can help with the customers. But I think in different times there may be more competition for them to produce their electricity. I think we're now in a position where we're able to fix our prices are more variable and at the whim of what's going on politically and globally, but maybe that will change in the medium term.
Yeah, I would like to add on here that it's important to make sure that we are not going blindly towards electrifying the heat demand, because of course that will have impact on the electricity sector. And one of the key things is exactly that when we go into electrification, then we don't want to have the peaks that is needed during the cold day of supplying that electrical peak. That can be extremely expensive in the long term.
Okay. No, that's very good. I'm conscious we're getting up very close to the time, so I'm trying not to cherry pick questions. But there was an interesting one from Mark Nichols about whether the 4G versus 5G is so given the predicted future move to refurbishments of buildings over demolished new build, is there any general benefit of one system over the other when implemented to existing buildings? So we've talked a lot about new build developments. When we're looking at retrofitting existing buildings with systems, do any of the speakers believe that the economics change between 4G and 5G, or have they not? Have you not considered that? Because generally you're looking at new build situations. I'm happy to skip on if none of the speakers, or Oddgeir's got his hand up.
We actually have made an analysis on the impact of low energy buildings. And the thing is that the centralizing the equipment actually can be a benefit towards the building solutions. Because of the capex, you have better possibility to scale down the capex compared to individual solutions. So it actually enhances the economics of the fourth generation.
Okay.
I'd add Yeah, so if you're looking at retrofit, you're most likely going to be looking at connecting to a larger network being developed in the area. So then the considerations you've got are either putting a plate heat exchanger for that 4th gen system, or a heat pump in the sort of basement plant room of that building, assuming that it has a wet system that you can connect into. So the considerations there with 5th gen is can you realistically, within the space available within the kind of plant room, is there adequate ventilation and power supply to put a heat pump in? So that there could be challenges there, but of course that can be worked around, compared to just putting a plate heat exchanger in, which may be an easier fix. But as it was mentioned earlier, you've got flexibility around temperature with putting a heat pump. So if it's an existing building with quite a challenge, it's being supplied at 80 degrees, and it would be quite difficult to reduce the supply temperature of that building. With an ambient system, it could just be a high temperature heat pump put in, whereas a 4th gen, if it's set at kind of 70 or 60 supply, then you're going to have to put that money in to be able to adapt to a lower temperature supply, or boost it locally. But yeah.
Okay, no, thank you very much indeed. I'm conscious we're a minute past the closure of the event, but I'm also conscious we've still got 100 people online asking questions. So if speakers don't mind staying online, we'll go on for another 5 minutes. Matthew, there's an interesting question from Hamish to you in the question session. So it says, Matthew, the losses you mentioned that were after the meter, does that mean that we're effectively moving the secondary network losses of the 4G system onto the resident in the 5G system? So are we, when you said that the developer doesn't have to pick up the cost for those, is the fact that the dwelling consumer is picking up the costs and they're simply not being seen by the developer? So what are your thoughts on that one, Matthew?
Yeah, I think my key for that one is the scale. So we're talking about a far smaller proportion of waste heat compared to a 4th gen, which has quite a considerable, or potentially considerable, you'll try and design it now down with modern design. The losses on a 4th generation network, and I think Asad gave some quantity to that in his comparison, they're quite a smaller scale, but they aren't the cost of that losses isn't put back on the ESCO or the network operator. It's billed and it's revenue generating. So it's on the user, and it is a smaller proportion compared to a 4th generation. It is higher though than a HRU working instantaneously, so it does potentially exacerbate issues of internal overheating, and there is a sort of a move to more onerous methodology of assessing residential overheating, CIBSE TM59, and that is a concern, and it's also a bigger problem more recently because of the changes in acoustic planning guidance as well. So it's harder for a residential unit to get through overheating, and when you're putting in a 5th generation local heat pump into that, you are going to be creating a slightly more difficult problem, and the issues you'll probably find then take you down the route of putting in cooling, which isn't or further requirements. So you do have to consider it, but in terms of scale, they are much less, but it's just a higher proportion.
Okay, right, fair enough. I'm conscious of not trying to cherry pick questions because there's an awful lot of them, and many apologies to the delegates who we haven't got to, but we'll need to close in a couple of minutes, so I know people need to get away. There is an interesting question from Chris Forster, which I think would be useful to discuss. So this, you touched on this briefly, Matthew. So it says, for 5th generation networks, what are your thoughts on metering and billing arrangements that are needed? The use of 5th generation networks and metering requirements are still unclear. So I'll be interested to hear on your views and what should be classified as useful heat. So this goes back to tenant costs and what they're actually metered for, and what typically should be an expected standard in terms of what's metered to the end customer and what cost the end customer picks up. Matthew or any of the other speakers, would they like to talk?
Yeah, I think I'll set it up and then others can answer. But I think Asad mentioned earlier, the standing charge on a 5th generation is sort of a bit of an inaccurate way of and a bit unfair sometimes to billing people. I see fifth generation networks, and the major benefits to them is more accuracy in billing and actual energy use, because you can have different benefits, and I'll come on to those in terms of the type, but it's got to be a dynamic metering system, so you're able to incentivize the use of lower cost or lower carbon heat from your waste heat sources if you have them in your fifth generation network, and that would incentivize and also bring down bills for certain users. So we talked about fuel poverty and things like that. They could do something in their behavior and their energy usage to reduce their bill if they use it at certain times when it's incentivized, and also discourage when not to use it. So the fifth generation and the local storage of domestic water does enable that flexibility as well for the user. But as I said, you'll need heat and flow meters for your local heat pump, and then obviously the customer will have their own electrical meter at their consumer unit that will bill the connection to the local heat pump that's off their local consumer unit. So that will all be part of their bill that they arrange with their own contract with energy providers. And then obviously centrally you would meter everything coming into the networks for your own generation, your central generation plant, and any waste heat sources. And the local customers, obviously, if they're discharging and rejecting heat to the network, would also be either not charged for it or maybe charged for it at a reduced rate potentially. So it is flexible, but I just open it up to the floor if anybody's got anything to follow that.
Any other thoughts just before we close? Asad, I saw you thinking, or happy to skate on to close the event. So I'm conscious we're 6 minutes overdue, so we really need to close.
Yeah, sure. I was just going to add that there's that added complexity when you introduce cooling and the potential for a customer to be prosuming, as it were, to be supplying into the network. I don't think the metering regs quite sort of caught up with that complexity, that you want to be rewarding them for supplying heat into the network, because they're offsetting some centralized generation. So that's a consideration in those types of systems. We've not really talked about cooling a lot today, but want to add.
No, absolutely. Well, I'm conscious we're very over time now, and I'm conscious that we've got lots more questions. So I will just ask the speakers, if you don't mind, if Tom pulls the questions down that we haven't managed to get to. If any of you feel that you can answer them, then we'll circulate the responses after the event, because I think we'd like to give a lot of respect to the many delegates who've asked an awful lot of questions today. So a big thanks to the delegates. A big thanks to all of the speakers. A round of applause. Brilliant. Thank you very much for some really interesting and stimulating talks. I think in just closure, I think the key takeaways for me are a project-specific analysis looking at 4G versus 5G. It makes more sense if you've clearly got on-site mixed heating and cooling. A whole life cycle cost is incredibly important. You shouldn't analyse just one part of the system, and it's incredibly important to consider costs to the end consumers. So thanks very much indeed to the delegates. Thanks very much indeed to the speakers, and we'll bring the event to the close. Thank you very much indeed, everybody. Goodbye.
Thank you.
Thank you.